we will talk to you about performance optimization tips and tricks for Unity. So the goal of this talk is to enable you to run your Unity content as fast as possible. So first, Kim will give you a tour of our profiler to show you how to find out where your bottlenecks are, where you should spend your time optimizing. And then we will go through different topics of the Unity engine and give you some tips and some general information on how to optimize for those. So anything we talk about here should apply to all the platforms we support. But if there's any platform-specific considerations, we'll try to point those out. So yeah, I'll now hand over to Kim. He'll give you a demo of our profiling tools.
Yeah. So when you have your game running in the editor, you can attach the profiler or open the profiler and get runtime information of how your game is doing. You can also do this on standalone players, on mobile phones, and connect to the editor, and you'll be able to profile your application directly from on the device without the overhead from the editor. Simply in the build settings, whenever you build it with development build and the auto connect profiler. Then the build will start up and auto connect to the editor, and you will get a view that looks a lot like this. So when you have your game running, and then you have your real-time profiling data here, where every vertical line is one frame, so being recorded. This is our demo project, Angry Bots, and it's pretty optimized already, so there's not much to find here. But in your games, you might be looking for spikes like this frame where it spikes a little bit, trying to eliminate those to prevent hiccups in your frame rate. You can see down here we have a drill down hierarchy view of that frame you're investigating. There's how much time the root is using, how much memory is allocated through mono, and you can drill down into these and see how much time is spent in these parts of the rendering, for example, the CPU side of rendering. Also, you can see user code, like the laser scope update takes a little bit of time. It actually allocates 20 bytes every frame. So you might argue that you could go in there and remove those 20 bytes. It's probably a class being allocated instead of a struct. So we've seen examples of games running completely without allocating any memory. Then we have the GPU profiler, where you, again for the same frame, can do a drill down in the draw calls that are happening. So you can see that there's 93 draw calls happening in this part where there's opaque, transparent draw calls, and you can investigate how much memory or how much time that's taking, and in that way get to let's see. Then you can see in the detail view how much each mesh is taking up each draw call on the GPU side. So having an expensive shader or having many polygons might trigger that that you have a very expensive mesh. Then there's the rendering and memory parts of the profiler, which give you some statistics on the frames and how many triangles, how many draw calls, how much memory texture bandwidth you're using, and that can also be a good source to optimize your code. And then finally, there's memory. It's not very extensive. You have a memory footprint of your application, and then you have some estimates on how much textures, meshes, and audio, etc. is taking up. So if you want to reduce the memory footprint of your application, this might be a place to go in and target. So I guess that's it.
Thank you. So yeah, now we will go talk about different topics of optimizing in Unity. First off is optimizing your scripts. So Kim has showed you how to find out where you spend time in your code using the profiler. So you should be able to you should know which of your scripting entry points you need to focus on optimizing. Sometimes that's not enough. If you have complex scripts, you will actually want to know where in those scripts you're spending time. And you can drill down into that by using the profiler.beginSample and profiler.endSample functions in your script code. So any code you brace between those functions will show up as a separate item in the profiler hierarchy. So you can see exactly which lines of code or which sub-function calls in your script are spending time. So at that point, you should know quite exactly where you need to optimize. Of course, optimizing scripts is mostly about optimizing algorithms, which is pretty much generic programming knowledge, and we won't get into that for this talk. But there's some Unity specifics some tips we can give you about script optimization. Like the way Unity is set up, you're encouraged to put all your logic in your script's update functions. And that means that your scripts will be called for each instance, for each frame, for each object you have it on. And quite often, that's not actually what you need. You may have a script which is doing some graphical effects, or which is showing some object or handling some object which interacts with the player, where there's no point in updating them when they're not visible on the screen. And there's a very easy to use callbacks to optimize for that. Just hook up the onBecameVisible and onBecameInvisible callbacks in your script. And you can just set self.enable to true or false, and those to turn on and off execution of your script whenever the renderer attached to the game object becomes visible or invisible. That way you can make sure your code only runs if the attached game object is visible on the screen. Another thing is that often you don't actually need to run your logic every frame just because the update function runs every frame. It's quite easy in Unity to set up an update loop for an arbitrary frame rate using coroutines. Like here's a code sample which shows you how to just set up a loop by making an infinite loop in the start function. And then in each loop iteration, you just call yield return, you wait for seconds with the time value. This makes the loop run every 0.2 seconds in this case. So you have your loop running at a frame rate of 5, or at an iteration rate of 5 times per second. So if you have any logic which doesn't need to be updated at your game frame rate, you can spend much less time doing it by a simple construct as this. One other thing we see a lot when looking at user projects is that people are unaware of the overhead of Unity Engine APIs. Especially like if you come from a C++ background like myself, the concept of C# properties may be misleading because often it looks like a simple variable access, but there may actually be some complex calculations involved. A good example is transform.position. It's something you use all over your scripts typically. And if your object is somewhere deep in the transform hierarchy, it will actually iterate through all the hierarchy and perform matrix multiplications to find out the global position of your object. So you can easily wind up with code which does much more work than needed because you call these getter properties all over, whereas you could just buffer the result, cache it once in the beginning of the script, and then reuse it. Or if you have if you have some values which are not expected to change, you should just buffer them in the beginning of your, like at startup of your script, and then keep them around. Yeah, these were some hints about scripting, but Kim is going to go into some more detail about specific to memory usage. So yeah.
Yeah. When optimizing for memory usage, there are mainly two different things that you want to optimize for. One is memory footprint of your application, so to limit the download size for mobile devices and applications. And the other one is optimizing runtime to not do too many allocations during your runtime game, to avoid both fragmentation, but also to avoid that the garbage collector kicks in, because that has a very significant time consumption and will create large spikes in your code. So to understand more about the memory model of Unity, we have the mono part of memory where all your game objects from code are allocated on the heap. There's wrappers for objects such as game objects, assets, the texture wrappers, stuff like that, and all this memory is on the mono heap and is garbage collected in time. There's of course the other side, which is all the Unity internal memory, which is all the textiles for textures. It's the audio data. It's meshes, animations. There's game objects, components. All the data for those are in C++. And for other internal systems like the multi-threaded renderer, the physics, the particles, etc. So in order to whenever you ask Mono for memory, it has a pool of heap blocks. So it has a pool of memory where whenever you ask for memory, it'll allocate from those. This is very fast. It just grabs a block, and whenever it goes out of scope, it just leaves it there. That can be really efficient, but if in time it will the garbage collector will kick in, and that's the part that's really heavy. So whenever the allocator runs out of space in these heap blocks, the garbage collector is called. It tries to clean up mallocs or allocations that are no longer in use, and if it can't find space for the allocation, it'll start allocating new heap blocks. So your memory footprint of your application will grow, and following garbage collections will also be slower, because it has to scan more memory for stray or dead allocations. Also, having a lot of this activity will where it allocates and deallocates memory a lot, you'll start getting holes in these heap blocks that are too small to fit your allocations, but they still take up memory. So you'll start fragmenting your memory and eventually run out of memory because you get so many holes in the memory. So the garbage collector is the bad guy here, and that will trigger on. It can trigger on any allocation, because if it runs out of memory, the garbage collector will trigger, and you get a spike at an arbitrary point in your game code, and that's not really desirable. You can control this a bit by calling gc collect at a control time, like a level load or something like that, and then get your spike in a place where it's suitable for the game. So in basics, what you want to do is avoid allocating memory. Have control over how your memory is allocated. And you say we're in managed code, so we don't really have any control of that, but that's not quite true if you look at some of the internals in C#. the main thing about this is that when you use classes and structs, there's a big difference, because when you use structs, the allocation is made on the stack, and whenever the variable goes out of scope, it'll free that memory again, and it's placed on the stack and not on the heap. A class, on the other hand, will be allocated on the heap, and it'll stay there until the garbage collector kicks in and cleans it up. So try using structs instead of classes, because that keeps your memory clean. I've made an example here with two workers, one that's allocating a lot of memory, and one that's doing the same job but without allocating anything. This one over here, it has a class work data that is allocated here, so it's put on the heap. It has a process work data which uses some temporary buffer where you need to, I don't know, process some binary data, filter some audio, something like that. And just doing here a small modification. On the other side, we have a struct for the work data. We keep the work buffer on the class, so it's allocated once and then reused every frame. And yeah, up here you can see the profiler that calls both the allocating worker and the deallocating worker, or non-allocating worker. And the allocating worker is taking a lot of time. Both the allocation takes quite a lot of time. It kicks off the garbage collector once in a while. You can see all these spikes up here. And it's in this column you can see that it's actually allocating a lot of memory, and that's why the garbage collector kicks in. The other one on the non-allocating has no allocation. It takes virtually no time because there is nothing to do here. Everything that takes time over here is allocating and running the garbage collector and stuff like that. So just reordering how you do stuff, you can actually get rid of a lot of allocations. Then you might have objects that you need over several frames, or they're not that temporary that they would fit on the stack, because they need to live for a certain number of frames. Then a trick is to pre-allocate a pool of objects and then have those on a list. And whenever you need an object, you pull that object from the list. No allocations, it's just getting a pointer. And whenever you're done with it, you put it back on the list. This way you can also you can gain a lot of performance, because you don't have to allocate and deallocate, and the garbage collector doesn't kick in. At Unity, we've made a small example project that's on the asset store, which is called Astrodudes, which uses this this way of handling objects. So you can see example code there. And this also goes for object instantiation, because object instantiation and destruction is also very slow. It calls a lot into Unity, and again, it allocates and deallocates a lot. So having objects that you need to spawn all the time and destroy, like bullets or explosions or stuff like that, again, put them on a free list, disable them, and whenever you need one, pull it from the list and enable it, and you have your object straight away without the overhead of having to instantiate and so on. So, and there's some gotchas in that you should try to avoid. Unity's GUI system, as it is now, is not very memory friendly. It allocates quite a lot, and that causes the garbage collectors to run way too often. And so in-game and runtime, don't use the Unity GUI. It's fine in menus and stuff like that, where hiccups are not that big of a deal. But it's actually possible to build your game without doing any allocations at all, and then you'll get a much more stable frame rate. So there are some APIs in the profiler that you can use to monitor Mono's memory, and that's get mono heap size and get mono used size. And the heap size is the total size of its working area, how much memory it has in its pool of memory to use from, and the used size is, of course, how much of this memory is currently being used. So if you try to keep these numbers stable, you're in a pretty good situation. You can also, to investigate if you have a large memory footprint of your application and can't really find the textures or meshes that are taking up a lot of memory, you can use the get runtime memory size of the objects, and then you get an estimate of how much this object is taking of memory. So if you have textures sticking out that are suddenly 4K by 4K, you should probably try to reduce the resolution or apply compression and stuff like that.
Thank you, Kim. By the way, there's still a bunch of free seats over here, so I see many people crowding over there. You might just move over here if you want to get a seat. So yeah, I'll have 2 brief slides on physics now. There's a few considerations for optimizing your physics code if you see that it becomes a major bottleneck for you. The first is whenever you set up your physics scene, always prefer primitive colliders over mesh colliders. Primitive colliders are much faster to evaluate than mesh colliders. So even if the shape of your objects may not match very well with like a capsule, box, or sphere, you can usually come up with some very good approximation which will essentially feel the same to the player by using a handful of those and still get much better performance than by using a mesh. Then if you're tweaking physics, the single most important parameter is the fixed delta time, which you can adjust in project settings time in the inspector. This sets the frame rate at which the physics simulation is running, because physics simulation in Unity is running at a fixed frame rate independent of the frame rate your game is running on. This is important in order to have consistent simulation results. But it also means that the higher the frame rate, the more often you're doing physics updates per second. Obviously, the more time you spend simulating physics. So you should go and try to tweak this value and see what's the lowest you can get away with. Of course, if you set this to a lower value, you'll find that the quality of your simulation will decrease. Especially, you'll find that collisions between fast-moving objects won't be detected very nice, or not at all, if you don't use continuous collision detection. So it really depends on your game. If you have a very fast-paced game, you may need a high physics frame rate. You may actually need a higher one than the default of 50 frames per second. But if you're just having a slow-paced game, you can probably get away with a lower value and spend less time in physics simulation. One more common gotcha when looking at physics, like we see this a lot in user projects, is that you should never ever move a static collider. So a static collider is, to the physics engine, a static collider is any collider which does not have a rigid body attached. Basically, for the physics engine, any collider which does not have a rigid body attached is not expected to be moved. So if you have a game object with a collider and you start moving that from scripting or animation, and it doesn't have a rigid body, then each time you move it, the physics engine has to regenerate this big data structure of where all the colliders are in the world, which takes a lot of time. So instead of doing that, you should make sure you add a rigid body to the collider, since if you may not want the object to actually respond to other physical objects in the world, you should just set the iskinematic flag on the rigid body, which tells the physics engine that you want to move this object yourself, such as by scripting or by using animation. So whenever you move a static collider like that, it will show up in the profiler as static collider.move. But unfortunately, which is a bit misleading, the actual performance hit doesn't happen when moving the collider, but it happens in the next physics simulation step. So you don't actually see the performance hit from this, but you can pretty much tell that whenever you look at your profiler output and you see the static collider.move line show up, You're probably doing something wrong, and you should probably fix it. Yeah, so now we'll get to the last section of our talk, which is optimizing graphics. Since a lot of content spends most of its time in graphics, this will also be the longest. So first off, some basics about graphics and performance. Rendering performance is mostly bound by two factors, which is like how much rendering the GPU can handle and how much overhead your rendering induces for the CPU. So GPU performance is mostly limited by two factors, which is your fill rate. Fill rate is how many pixels the graphics card can render per second. And by memory bandwidth, which is how much memory you need to pull in to render your scene. And the limiting factor for CPU performance is the overhead induced by draw calls. Like whenever anything is rendered on the screen, the CPU will set up all the state for the material you're using and then send your meshes to the GPU to render. And each of these rendering commands is known as a draw call and induces an overhead on the CPU. So Kim showed you how to use the GPU profiler to see how much time you're spending on the GPU for each draw call. So that should give you a picture of like where you need to optimize. But first off, let's look if there's any of these draw calls you can just get rid of, because often you find that you're drawing more than is really absolutely necessary. And only after that, we'll see how to make your rendering perform as fast as possible. So, well, you can render fewer objects, obviously by making your scene less complex. But, well, you probably don't want to simplify reduce the fidelity of your scene. So there's some other things. Like first, Unity uses culling to make sure it only renders those objects which are visible. It uses frustum culling to make sure that it will only render what is within the viewing angle, and it uses and within the viewing distance. So those are parameters you can set up on your camera. And you can enable occlusion culling. Occlusion culling detects when any object is occluded by another object, so it's not in sight, and will turn off rendering for it if that's the case. So if you're not using occlusion culling, you have to set up your scene and bake the culling data in order to use it. You should give it a try and see what it does for your game. Whether or not this gives you big gains depends a lot on your scene. If you have a closed environment, like indoor environments with a lot of walls, then you typically have a lot of occlusion, so you get very big gains by using occlusion culling. Whereas a more open world environment may not give you many gains at all, or even run slower due to the overhead. So if you're doing a flight simulator, occlusion culling may not help you very much. But this is also something to keep in mind when you're designing your levels. You can get much better performance by designing your levels with occlusion in mind in the first place. Then there's LOD. Unity 3.5 introduced the LOD group component, which you can use to enable and disable renderers based on the size of an object on screen. So you can use that to use simpler representations of objects as they are further away or not render them at all. So yeah, this should help you get rid of some things you don't actually need to render. Another thing is you should be aware of that many things in your scene setup actually will cause your objects to be rendered multiple times. Like if you're rendering shadows, all the objects affected by the light will be rendered into the shadow buffer. So that induces one draw call for each object hit by the light, so your objects get rendered multiple times. The same if you're using pixel lights in forward rendering. You'll add one rendering pass for each mesh affected by each light. So this can add up quite fast and make your scene, make your rendering work much higher than it needs to be. So you should have this in mind, and especially when setting up lighting and shadows, you should always prefer pre-rendered light maps instead of real-time lights when you can, like when you have static geometry. This will give you both better quality and faster rendering. Also note that you can adjust the pixel light count, which is the maximum amount of pixel lights used on any object in quality settings, which is has a very big impact on your rendering performance. So yeah, now let's see what we can do to make those objects you actually need to render as fast as possible. So as we said before, CPU performance may be limited by the amount of draw calls you need to process, and the overhead introduced by those. So as a general rule of thumb, you probably shouldn't be using more than a few hundred draw calls per frame on mobile devices, or more than a few thousand on desktops if you're targeting current-gen hardware. If your numbers are much higher than those, you probably have some work to do in optimizing your draw call count. So what you can do to lower your draw call count is to combine your meshes. If you have multiple, like as I said, each mesh sent to the renderer is one draw call. So you can combine multiple meshes to be one big mesh, so it can get sent to the GPU in one thunk, as long as all these meshes use the same material. So you can do this either manually in your source assets by making sure that your models contain as few separate meshes as possible. But Unity can also take care of this automatically. It has static and dynamic batching. Like static batching, what it does is whenever it loads a scene, it will combine all the meshes marked as static into bigger combined meshes. And the dynamic batching essentially does the same for dynamic objects as they're being rendered. But there's some considerations to follow to make batching efficient, which is you need to use as few different materials as possible, because only meshes of the same material can be batched and rendered together. So make sure you just find a handful of shaders which have all the capabilities you need in your scene, and make sure you use as few different textures as possible, so you can get away with using few materials. So what you should do is, instead of having like lots and lots of small objects and each of them has its own texture, you can just generate big atlas textures where you combine all these textures into one texture and use those for your materials. And that way you can ensure that Unity can do the best job possible on batching. You should know, though, that this only really helps you when you're actually bound by draw calls. There's a common myth that optimizing graphics is all about optimizing draw calls, and that doesn't really hold true, especially for modern desktop or console hardware, which is generally very fast and can handle a lot of draw calls. So in the worst case, this can actually make your scene run slower, because the bigger combined meshes, because they're bigger, they're more likely to be within your culling volume or be affected by light. So you can end up actually having more be rendered. So let's look what we can do on the GPU side to make your rendering as fast as possible. As we said, GPU performance is often limited by fill rate or memory bandwidth. These two are easy to check for. If you run your game at a lower resolution, which means that it has to render less pixels each frame, and that makes it run faster, you can assume that you are fill rate bound. Because yeah, it has less pixels to render, so you have less fill rate you need to push. Likewise, if you want to test whether you are memory bandwidth bound, like the main memory usage for rendering is typically the texture data. So if you go to quality settings and you reduce your texture quality, which makes the textures used smaller, and that makes your game run faster, then you're likely to be memory bandwidth bound. So let's see what we can do about these. If you're fill rate bound, the main thing you can do is try to reduce the complexity of your shaders, because the more simpler your shaders are, the less work the GPU has to do per pixel it renders. So some hints on that. If you're targeting mobile, um, note that the alpha testing shaders are typically very slow to handle for mobile GPUs. So avoid using any of those and use alpha blended shaders instead. And in general, if you're using our built-in shaders, note that we have some optimized versions of these labeled with the mobile prefix, such as mobile diffuse, mobile bump map, etc., which are optimized, simplified versions of the normal shaders, which generally have very similar output but are faster to execute. And unlike the name implies, these also may give you better performance on non-mobile setups. So you could also try them on those. If you're writing your own shaders, there's some considerations on how to make them run as fast as possible. One is that you should avoid using too many expensive math functions. So if you're using a few of those and you only have like 1 or 2 input variables, you can probably evaluate the results much faster by simply rendering them into rendering all the results into a pre-calculated texture and using a texture lookup instead of doing the calculations in the shader. And if you're targeting mobile, you should be aware that mobile hardware is very sensitive to the number precision format used. Like if you're writing your shaders in CG code, you can declare your variables as either float, half, or fixed, which is different floating point formats. And mobile GPUs tend to be much faster processing the lower precision formats. So you should just experiment with what's the lowest precision format you can get away with for your numbers, which still achieves the results you need, and use that for best performance on mobiles. When you want to optimize memory bandwidth usage, you should mostly look at how you can get your texture memory usage down. So you should make sure that you're using compressed textures for all your textures where it makes sense. You may find that compressed textures give you some compression artifacts, especially for GUI textures. In those cases, you could try using a 60-bit RGB textures instead of 32-bit, which is still saving you half the space. You can also see if some of your textures are simply too big, and you can get away with making them smaller. If you go to the scene view, there's a feature called a mip-map rendering mode, where as you move your camera through the scene, it will shade your scene in blue or red, depending on if the texture size used on your scene is appropriate for the current camera position and view size. So by moving your camera around in the scene view in mip-map render mode, you may find that some textures which stick out to be like candidates for optimization by using smaller textures. And generally, make sure that you always enable mip-maps for any textures you use in the 3D scene, because that allows you to use the smallest representation needed. One more thing about GPU performance. You may find that it can also be bound by the geometric complexity, which is the vertex processing done on the GPU. Like the vertex shaders processed for each of your vertices. So if you want to optimize for that, make sure you don't use more triangles than necessary. You should keep in mind that whenever you have UV seams or hard edges, like when you have a vertex which has multiple different UVs or normals, these are treated as different vertices for the GPU. So you get the vertex processing overhead multiple times. And basically everything I said about shaders for optimizing for fill rate also applies for vertex shaders. So yeah, that concludes our talk. So now we are available for Q&A. So if you have any questions, fire away. Yes, over here. Yes. No, the memory overhead Kim was talking about should only apply for the current one. And it's one of the reasons we need the new GUI system fast. But I think your question was already answered, right?
Hey, over here. So, can you tell us what happens with the memory when you initially load something in the scene? So, if you then instantiate an object or stuff like that, so so give an example.
Yeah. So you're talking about whenever you instantiate objects and you create game objects, and
Okay, so I remembered. So if you have an object but you don't show it in the scene, do you load the texture when you load the scene, or do you load the texture when you show the object? You have an
so if you have an object or a texture in your scene, and you unload the scene, but if you're still referencing the texture from script code, then it won't unload that texture because it's still referenced.
Yeah, but do you load it in the memory the first time you load the scene, or the first time you show the object?
It's loaded into memory the first time when you load the scene. It's not uploaded to graphics memory until you actually display the object. But that's GPU memory.
Okay, thank you.
Hi. On the subject of Atlas textures, I have a game which uses a lot of small textures. It's a mobile game. And I like to tile the textures because it's a texture, like a grass texture. Is it possible to use an Atlas texture and tile those individual textures as well?
I don't think it is, unless you may have a very smart custom shader doing the texture lookup. Yeah, I guess it would be possible doing that, but the normal texture wrap modes don't really work well with tiling, yeah.
So it might be possible with a custom shader to get the UVs.
It might be possible. I don't know if the extra calculations will then give you any performance gain. I mean, in general, you should, I mean, this only applies if you're actually bound by a draw calls, so there's... There's some testing to do whether this is where you need to optimize or not. But if you see that using less draw calls will make you run faster, then there might be some experimentation if there's anything worthwhile to get out of this. But yeah,
okay.
Your mileage may vary.
Yeah.
We're developing not a game, but augmented reality applications. And in one of those applications, we took a picture of the background video image and then used that as a texture. And it appeared that the texture wasn't actually freed until the next level was loaded. Is that something that you can confirm? Or?
Yes, it's because whenever you release your assets and textures and lose the reference to it, if the garbage collector was then run, then you would actually get that texture unloaded. And if you're reusing this texture, then you would get a missing texture, or even worse, you would start loading it from disk. So we keep all assets around until unload unused assets is called. It's kind of a garbage collection of the assets in use. And that is also called whenever loading a new scene, so that's why it disappears at that point. But you can also do the cleanup yourself by calling unload unused assets.
Hi, I was just wondering about, with iPad 3 has a Retina resolution, so the fill rate's pretty high on Retina. You said that Unity 4 is going to support some kind of native upscaling, is that right? Like half rendering and upscaling to iPad 3?
Yes, we do that. I think it's a new feature in Unity 4 how we handle resolutions on iOS, that we give you the option of rendering to a lower resolution buffer and upscale that on blitting. So that enables you to get like better performance by using less fill rate on those devices.
Can you achieve something similar with a render texture in a scene and just kind of rendering it to a plane to reduce fill rate? Is that something you can do with the current version of Unity? like besides doing the native upscaling, just using like a render texture?
I guess you might approximate it to some degree. Yeah,
But is there some other overhead?
It's whether or not this will give you gains. I guess depends on your game and on your scene. But it could, I guess. You might want to talk to our mobile folks in the Q&A sessions for more details on that.
Okay, thank you.
By the way, both of us will be at the hands-on labs later. So Kim will do hands-on on performance, and I will do them on physics. So you can also come up there for detailed questions. But we'll still be around here for 5 minutes. So
yeah. So yeah. Mics.
Hello. I apologize. I have 2 quick questions. One, outside of the GUI side things, are there ways to increase the performance of skin mesh rendering? For example, would dynamic bone reduction via script be helpful? And the other question is, what special considerations should there be for Flash performance?
So the first was how to optimize the skin mesh renderer.
And animation in general.
Well, I mean, I guess there's not much specifically you can do to make it run any faster, other than making as little use of it as possible, like making sure your models don't use more vertices than needed, and making sure you can set up how many bones affect each vertex, which of course makes the calculation faster. But other than that, we have very optimized paths for that. For most are written in assembly for different target platforms. So I think we're not doing GPU skinning right now. That may be added in the future, but yeah, I couldn't give you any other hints than making sure you're making as conservative use of it as possible. And what was the other question?
What special considerations should one take into account for Flash performance, other than the naive things like reducing draw calls, bandwidth, and things like that?
I think you should probably talk to our Flash team about that, because there are stuff that is not really working well on Flash, but I'm not sure. I mean,
I think in general, when you're targeting Flash, the GPU is not so much your limiting factor or the rendering, because it still has a very fast GPU attached to it, but the CPU code, especially things like skinning, running in a virtual machine, are much slower than on other implementations. So I think when you're targeting Flash, probably you have less of a rendering focus on optimization than on other platforms. But that's all I can say about it. But you can find our Flash people and have probably get a much more detailed answer from them.
I think also the multi-threaded render is not running on Flash, so you get all your render. The CPU side of the rendering is actually happening on your main thread. So,
thank you.
Hi. We're currently building a game, or multiple games, for iOS, and our artists love the Strumpy shader editor. So on one hand, we have a drag and drop interface for building shaders, but on the other hand, it creates some overhead for mobile devices. Can we expect in the future, I don't know, like a native Unity shader tool, or I don't know, shader optimized helpers that will actually show you what you're doing wrong or something like that? So more visual approach for the artists.
We're always trying to improve our performance tools, but it's not anything that I know we have in the pipeline. But yeah, using.
Well, we will have GPU profiling on Android for Unity 4.0, which should help you a bit figuring out which shaders you need to optimize on mobiles. So that's not exactly like helping you directly making your shaders, but it's going to help you like drill down to what you need to optimize on.
Yeah.
Thanks.
Hi. What you said earlier about we should not move static collider, does that mean it's better to have hundreds of rigid body in the scene?
Yes.
For example, for each enemy and bullet, even in shooter game?
Yes, if you have any colliders and you're moving them, you should have a rigid body. I mean, if you're talking about enemies, you might have a character controller for those. That's actually a special case because it's like a collider with a built-in rigid body. So that one is treated special. So, but for any of the normal colliders, if you move them, put a kinematic rigid body on them. Yeah.
Thank you.
Hello. Is it true that the current mono version does not use a generational garbage collection?
Yes, that's true.
It
It does some incremental collection a little bit during every malloc, but the generational garbage collector is not in that version.
Okay. Do you plan to update that?
I don't know if it is in the version that we're looking at.
I think it's some vague future plan, but we can't give you like any dates or anything. But
okay, 4.0 maybe.
No, that's not the vague future.
Okay, there's a memory profiling option. It's profiler.heap size, I think.
Yeah.
Can that be used in the web player build?
Yes, in a development build, yes.
Oh, okay.
All profiler APIs are stripped in non-development players.
Okay, that's cool.
And the profiler is also a pro feature. Just.
Thank you.
Hi. So I have a question with regards to textures and explicitly non-power of 2 textures. I tried to write an edge detection algorithm which sort of traces the edges of, say, a pixel bitmap, and it extrudes them back. But I noticed that when I'm using non-power of 2 textures, the edges become considerably different to when I'm using the exact same, but with sort of alpha padding around it. Is there anything that you know of kind of internally that might help there?
On certain platforms, non-power of 2 textures is internally handled as the next power of 2. So there might be
that would probably be the reason. Yeah. But I guess our graphics guys would be able to explain more. But I think it's like that. It will use a bigger power of 2 texture, and
it's on the roadmap. Okay.
Oh, cool. Thanks.
There's one more over here.
Hi. While working with shaders, I stumbled upon a particular behavior where...
Where's somebody talking? Okay.
I stumbled upon, while working with shaders, I stumbled upon a particular behavior, especially on iPad 1, where the same shader, which made the exactly same calculations, both on the vertex and the fragment. One made the fixed function, the other with OpenGL 2.0 in HLSL. The fixed function one was really faster than the other. And do you think that is hardware dependent or software dependent? Maybe a driver problem or different ways in which...
I'm not quite sure of the differences between both OpenGL and DirectX, but that shouldn't matter because they should map to the same instruction. But hardware can definitely be an issue. But again, I know our graphics guys will know what differences there are, and especially going. You said down on Android.
What?
Did you use Android or?
No, I was using iOS. Yes, it was on iPad 1.
Yeah, but drivers, also ATI and NVIDIA, there's big differences between. But seek out our hands-on graphic guys, and they might have some specific for you.
Thank you.
Done there?
Hi. I have a question about alpha testing versus alpha blending, which you talked about. alpha testing would be less performant on mobile, so we try to use alpha blending. But when using alpha blending on planes that are quite close to each other, sometimes you get kind of like Z buffer fighting, where it just flickers between the two planes, the two textures. So question A, is it possible to prevent that with alpha blending, or if not, how bad is alpha testing really on mobile? Is that
how bad it is probably just a matter of trying out. It depends on, if you're not fill rate bound, you may just get away with it without any performance hit, right? So, and the other thing you might consider is because for alpha blending, you always render the whole area of the texture, is to simply have a more complex mesh which sort of represents the shape of your object. So you'd only have, see those artifacts. It depends on your assets whether or not that is feasible, of course. But yeah,
you can also
that's all I can think of.
You can also try adjusting your near and far planes, because that will change your resolution in the visible space.
But so that set index fighting is expected behavior when using alpha blending?
The set fighting?
The Z fighting, that you have the flickering between the two planes, that's because it doesn't happen on alpha testing? At least not with the built-in Unity shaders.
I think somebody would have to look at your project in detail to figure that out.
Okay, thank you.
Shall we cut it off, or shall we give it? Or shall we say one more?
One more, one last question, I think.
Okay.
And the ones that still have questions, we are in hands-on labs, so you can still come up and ask us during the next 2 days, today and tomorrow. Yeah, all 3 days.
Can I ask a question?
Yes.
Does destroying or disabling?
You're looking the wrong way, but
if you destroy or disable a static
Okay.
collider,
Can you speak into the microphone?
if you destroy or disable a static collider, does that count as moving it for performance of rebuilding the static collider structure?
Yes, if you destroy or disable a collider, that would also induce a rebuild of that structure. But it's it depends on what you're doing. But moving colliders is something games would typically do every single frame, so it's a constant hit. Whereas if you destroy it, that's typically just the result of an action in the game. So so you'd only take the hit once, which may be more acceptable. You'll see if it actually shows as a spike, which is big enough that it would appear as a hiccup in your game, then you shouldn't do it. But probably you can get away with it if you just destroy colliders or create them based on user action. But if you see a hit resulting from that, you could also get rid of it by using rigid bodies and those. Okay, thank you for listening.
Sorry about that. You can catch up with them later.